starting our next block. We're going into some more safety critical. We have 2 talks and a panel on Rust, the safety critical systems. But first, I would like to welcome Rolland Dudemaine from Trust and Soft and my colleague Aïssata Maïga to be talking about software verification. Aïssata is one of our Ferrocene delivery team contributors, and Rolland is working with Trust and Soft about software verification. So they will talk to you about making software safer, more correct, more efficient, all the things that we love to do with Rust.
Good morning. So, all right, that's not too close. So we're going to talk about validating Rust in the industry, which is different from testing. If you realize, it's not about doing it right from the engineering perspective, but doing it right from the process perspective. And especially when you need to reach certification, that's a topic. I don't know why, but this doesn't seem to work. It does? It doesn't. Interesting. So, why? Okay, now it works. Thank you. So my name is Rolland Dudemaine. I work in Trust and Soft. As said, I'm responsible for technical pre-sales for Europe and Asia. And actually, I'm just back from the Rust China conference, which was interesting as well. Trust and Soft, in case you don't know the company, I will present it in a minute. One key aspect is that it's a 13-year-old company, and we've been participating in the Safety Critical Rust Consortium, which I'll talk about in a minute. So again, all going into safety and security critical.
And I'm Aïssata. I work at Ferro Systems. I did different things at Ferros. Now I'm at Critical Ops or toolchain manager. And please go on.
So the Safety Critical Rust Consortium, it's a group of industrials where the intention is to define how to use Rust in mission-critical systems. That will go from, again, process definition to best practices to coding standards to, well, the end of everything you need to do to be able to consider that your software has been developed properly according to safety standards. Some members include Ferro System and Trust and Soft, which has a typo. Don't use the hashes. I thought I corrected that anyway. Ada Core, ARM, Woven, Oxidize, so it's all around the world. So one of the topics that was discussed recently, for example, is MCDC coverage. Another one that's coming up is coding rules, and so on. Trust and Soft, it's a French company. The company was founded 13 years ago by some people who implemented or heavily contributed into the implementation of PRAMA-C, which is a formal verification framework. Basically, they took on the mission to help customers not just find bugs, but prove the absence of several categories of bugs, which is very different because pretending that you find things is interesting. Helping you demonstrate that there's nothing left of the category of bugs remaining is a different level. And especially we focus on what would be called in C undefined behaviors, and I'll call that now runtime errors in general. The way the tool works is it applies formal methods and specifically abstract interpretation. I've had many people ask me about symbolic execution. Can mention that in a minute if you want, but it's 2 different approaches going top down instead of bottom up. Let's talk about Rust. I mean, Trust and Soft has existed for 13 years, so of course that predates Rust. So the focus was C and then C++, and now we added Rust, and then looking at Rust, basically we tried to understand what we could bring to the market in Rust. And Rust actually is a great language. And I'm a convert. I was using C before. What remains in Rust to be solved is actually the fact that the code can still panic. So panic is a deterministic state. But if you're in mission critical, and I mean mission critical like a rocket or a train or a car that runs and you can't actually afford to just crash, we're not talking of availability, but really mission critical, then panic is a problem. You still need to find the origin of those and eradicate even the possibility to do panic. In the best case, and if you can't, well, you need to basically find out at the system level what to do when you reach it. Other things that are actually defined behavior in Rust are overflows. Like signed overflow is something that wasn't defined in C, it's now defined in Rust, and that's great. You probably are doing something very strange if you have computation overflows in your software, and probably you want to not even have those. And so we switch from a discussion about undefined behavior to unwanted behaviors. So you could think that, well, yeah, that static analysis tools do that, Clippy will help. That's true, but in fact, actually, there are situations where those calculations will only happen at runtime. So, and that's where, again, Rust ups the game a lot, but you still have those events where at build time, it's difficult to figure out what would happen. The other one is unsafe. Well, of course, don't use unsafe until you use unsafe, but don't use unsafe. What I call unsafe is the power to shoot yourself in the foot, because it's actually you're taking back the power from the compiler to tell it you know what you're doing, and when you know what you're doing, you become responsible. And that's fine at the engineering level, but can you let your developers as a program manager use unsafe? Of course not. Because that means your weakest engineer will start to use unsafe and basically make your entire application go boom. But there are good reasons for unsafe. So basically you need to somehow find a way to confirm that unsafe is not a problem. Testing, static analysis, and maybe more. And then, of course, there's the case, which I see a lot in the community, that, oh yeah, let's rewrite the entire world in Rust. And until that happens, you still have to manage FFI. You still have to have Rust call other non-Rust code and have other non-Rust code Rust. And cross that barrier or cross that frontier, what happens? Well, you're still responsible for it. So you still have to figure out a way to test that. And the bottom line is Rust pushes you in the right direction, but you can still write bad code. And I do write bad code, and the first code I wrote actually was horrible, and it did not have any warning, but it crashed. Well, sorry, it panicked. So Trust in Soft Analyzer, it's a static analysis tool because it does not require the access to the final target. It does not even require to build. It does require that you have a trace of the build so that basically the tool can analyze your software in the same way that you would build it in release. Originally, it was designed to work on C. Then we actually, so for the technical ones, we parse the source code, create an AST, and stop at the C level to be able to keep all the semantics of the C language. And in Rust, we stop at the THIR level so that we keep also all the typing system and the benefits of the Rust language around. And then from there, it's basically trying to get, it's starting from that graph of the code and then enters input and then go through graph traversal. The approach is interesting because it's math. It will be able to understand, like Miri, single values, but it will also be able to figure out from your entire API all the possible inputs, and it will do all the combinations of all the possible inputs over the entire graph of your application, and then tell you what could go wrong. In safe and unsafe, that means figuring out if your code can ever panic, even before it runs. In safe and unsafe, that's the case. In unsafe, it will allow you to find also undefined behaviors, because there are still some in unsafe. And when you go through unsafe to call the rest of the world, then that's where it becomes even more interesting, because it will be able to do a single analysis that goes through the Rust code and then go onto the C and C++ code and back, or vice versa. It's the combination of those languages that actually makes things really interesting, because the invariant, the assumptions that are described on both sides can then be dynamically verified. And I say dynamically because the tool will really do a simulation of the dynamic behavior of the symbols during the execution. There's an interesting one top left, if you can read that very idiomatic Rust code, which honestly is just at the level of where I could read it and understand it as a C convert. Well, the thing is that actually can just break if you don't consider all the possibilities. As a reviewer, I would probably miss it. But then with that kind of tool, it will identify that there's a possibility that if the UA takes a particular set of values, it could lead into an overflow that you don't want. Again, unwanted behavior here, but fully defined, still not something you want. And if you can read bottom right, you see that the tool actually did not consider single values. It also shows you in a kind of special debugger which values were considered for that n variable and the accumulator, and then what would be the resulting set of values and what could go wrong, and in that case there would be an unsigned overflow. And so that's how the tool will lead to these kind of reporting alarms. It's not just telling you there's something, it's telling you there's something with that context, with those sets of values, and allows you to kind of debug to understand the complete context. It's the ultimate trace. And so what is detected? Well, unwrap is the obvious one, because unwrap leads to potentially panic. Expect, and then slice out of bounds, string, and integer underflow, overflow, and then because the tool is able to report those alarms, but because it goes through the graph traversal, it will write down also, or remember each state of each element there. And as a part of the output, it can output also a coverage report. So what's nice is now you could use the tests that you use in cargo tests, for example, or more generalized tests with complete API verification and get a complete coverage report that goes up to MCDC. We have already a proposal for MCDC for Rust. It works. Technically, we can explain how it works and so on. Is it going to be the official standard? Well, that's the discussion. But still, we can practically do that. So here it shows the division by 0, which is another way to look at things. And you see that the report actually, interestingly, shows C code and Rust code together in the same report. So if you can then make a composite report of your entire application, not just a module or a crate there. Are you doing that one, or am I?
No, that's a surprise from marketing. PowerPoint karaoke now.
All right, so that's an example of the unsafe coding rule example, which is actually a joint work we're doing with Pharos. And so what you could see in one of the coding rules would be that memory mapped MMIO accesses should be accessed in a particular way, and that the prerequisites should be verified. But the problem is they're mutable and dynamic pointers even. So there's not always a way to figure those out at compilation time. And so that's one great example where Trusted Soft Analyzer will be able to figure that out dynamically. The definition of those rules and the verification in the tool is actually an ongoing work. It's a big work. And the rules are updated and will be updated as the Rust language evolves itself.
Okay, thank you, Rolland. Every time I listen to this guy, it's a new presentation. That's very fun. So yes, I'm here on the side of Pharos Systems, and so this is to present our company. I think most of you know Pharos. So we are trying to enable Rust for new industries, not only safety critical, even if safety critical is very important in the case of ferrocene. And then there have been a lot of arguments with our colleagues about the point 2, but yes, how to present that best. We did a lot to bring new capabilities to the Rust ecosystems. And I'm very fortunate to work with great colleagues. Like we all love Rust Analyzer, and my colleagues also created the Rust Embedded group, which did a lot of the crates that we use in Rust Embedded. And I'm so fortunate that I almost never touch C in my embedded work, so this is thanks to them. And then, of course, we're here today to speak about ferrocene, and this is to bring, safety critical and the modernity of Rust to the safety critical world. Can you please? Oh, okay, thank you. So what is ferrocene? So this is the first open source qualified Rust compiler, and I think I was not in the room that day, but it started with the feeling that Rust is great. What do we need to do to bring it to safety critical? Can we make it official somehow? So so this is a SDK, so a whole pipeline that we did for different Rust versions. I'm going to show that later. Including airgate that we're working on now. It's certified by TÜV. Do everyone know what TÜV is? Oh, no. Because I learn that word every time, and every time I mess it up. So it's an organization that looks that certifies that what we do is up to European standards, and it's
Don't even try.
Okay. TÜV, please Google it. I was hoping that everybody, TÜV, of course.
It's basically an external assessor that will verify that you're doing the right thing.
With a German name. So this is certified by TÜV. We have signed release, so the code that you're going to use in ferrocene is going to be signed, so you also pay for that somebody is actually responsible for if something goes wrong, that it won't go wrong. And then we have a very strong commitment to upstream, so if there is a bug in ferrocene, we'll try to not fix it. Misunderstand me right, we're trying to fix it in upstream and then pull it down to ferrocene, because this is something that we really try to keep the Rust spirit to be open source, to contribute to open source, and this is something that we take very seriously. This is something in our development time. We have a big chunk of time that is allocated to open source development, and we have those projects that we really care for and that we contribute to. And then, ferrocene, we follow the Rust train alignment. That will come later. So another contribution that Ferrosystem did was the FLS, the ferrocene language specification. So it was originally developed by the ferrocene developers. So it was 6 months grueling work to describe the Rust language and then go through all the numerous tests and annotate them to see to what specification they are applying. We also test extra targets, and now this FLS has been adopted and is now maintained by the Rust project. And it's important to trust in soft, right? Because you're using it for the Rust plugin. So this is also something that Ferrosystem did. That's the ferrocene release train. So please don't look at the number because it started at 168. But basically we follow the Rust release train, and every 2 release of Rust compiler, so 12 weeks, we have a release of ferrocene. And in every release of ferrocene, we pull in every change of that lands in the Rust compiler. Plus, of course, the extra targets and extra testing assertions. So concretely, it means every day, 5 a.m., 120 PRs to merge. I was in that team. Heads up to, high five to that team, you are the best. So Ferrocin as a product, so we have like two main for the customers that want everything taken care of. So the SDK side on the right. So CI/CD, SBOM, authentication. Then we support private crates as well. So it's a crates.io that is quality managed and secured. We have, of course, automated testing. We have a database of those known problems, which is all the unsound behavior that is known in the Rust compiler that is going to be the next slide, but it's also something that we do. And then on the left side, for customers that don't need the whole pipeline, we have the quality managed components, so core hipless, the compiler, and then some tools that Feroce has built and is quality managed now. So Knurling toolset, which is embedded. Tools for embedded Rust and Rust Analyzer, and of course, like down you have the certification. So today, Ferrocin is qualified for automotive, medical software, and IEC 61508. I will leave Soner talk about that. And yes, we have the certification, the qualification is something that we can do, and when a customer approaches us, we can always look and qualify the target to the standard that they need. Yeah, so this is the famous known problems. So the job here is to go through all those unsound issues of the Rust compiler, try to describe them succinctly. So I think this problem is
boring.
No, the solution is boring. The solution is boring. The problem
it's necessary, actually.
Is nasty mangling. If you have two functions that have almost the same name, they can be mangled and confused. So this is completely unsound. And the solution is boring. Thank you, because the workaround is do not declare external function and statics with pre-existing names. So this is just to say that there are always going to be bugs in software. We just need to know where they are and document them and give information to how to contravene them. This is also a surprise from marketing. So in that partnership that we have, so I think the important information here is that it started like very recently, but getting along well. And the very important thing is, of course, memory safety is not optional in the world today, and compliance and confidence is where we want to go and where we want to bring people to. So we have both our companies have this strong commitment to correctness, memory safety, not just flag issues.
So it's really a situation where I had at the Rust in Paris event, there was an interesting one where one quality manager was saying, Rust seems to be really great because when I talk to engineers talking about use Rust, they listen to me. They care about actually all the quality stuff that I was trying to push them towards, and now they do it. And really that's the situation there, is that you need to do a good development, you need to define what you're doing, you need to make sure that you use tools that are qualified or valid for use, and that's exactly what Feroce is doing. Then you need to verify them properly. Verifying them properly, there's a huge amount of tooling already available in Rust, but it doesn't go to the end of it, and probably will never be. And so you need additional tooling that helps you to do that last 5, 10, 20%. So that's where we are. And again, that's to make sure that there's nothing left unturned.
So this is the conclusion to last slide. So basically I think everybody knows the graph. On the left is the cost of bug. The latest is discovered in the system, the more expensive it is. So Ferrocin and Trust in Software we are Trust in Soft Analyzer and Feros and Trust in Soft. We are 2 steps of a long chain of certification. So first a qualified compiler for certified code, and then all the power of formal analysis.
Yeah, and the analyzer is already qualified for the C language, and we're going to certify it, to qualify it for Rust whenever we've done a sufficient amount of work.
Yeah, so you can still write bugs, but we are trying to make it hard for you, yes. And thank you for listening to our talk, and please come to talk to us, come to talk to our colleague.
Questions?
Thank you, Taylor Swift.
Any questions about the formal verification process? About Ferrocene certified here?
Maybe I overheard or misunderstood the part where you mentioned it, but is there a real formal proof that there are no errors in the code?
So for some definition of proof and for some definition of error, yes.
Are we talking about what marketing calls proof or what mathematicians call proof?
Okay, so what we do is we have, the tool is sound. The property of soundness is basically to demonstrate that for any possible occurrence of a particular issue, the tool will detect all of them. So that we do a verification that for some category of bugs, the tool will find all of them. Then there's the tool, and then there's how you use it. If you use the tool sufficiently, then you reach all the paths and you used all the possible inputs into your software, then you make a demonstration that you found all the bugs. If the tool does not report anything considering the code and all the inputs, then there's a demonstration that there's no longer that kind of category of bug. Does that mean that there's no bug at all? Of course not. You can still have the authentication bug that was mentioned earlier.
But for that claim that you just made, there is mathematical proof.
Correct.
Okay, thank you.
Correct.
Over here.
Maybe as a follow-up, can you actually define your own goals to prove, or is it only the predefined goals?
Thank you. So that's something I didn't want to go too much in the details, but in the field of formal methods, there's a common one, which is proof. What proof usually entails is you have a specification in a formal language that you have to write, and then code optionally, and then it's basically model checking. The problem of model checking is nobody wants to write the spec because they don't know, because they have existing crates or dependencies. They don't want to create the spec for those, and that's impractical. And it doesn't scale. So instead, the way we approach it is, again, for a certain category of bugs, what we do is we do a dynamic analysis by using just the code. And then it's an abstract interpretation and figuring out if there are runtime errors. It will not prove that the code is functionally correct. It will prove that there is no path that leads to a panic, an unwanted behavior, and so on. And you know what? For functional proof, just do testing. That's fine. You know how to do testing. Cargo test or whatever. So that's the answer. That said, we have an engine to do proof, especially on C. It works, and we have customers using it. But usually they take the gigantic amount of code which scales, and when I say gigantic, it can be up to the million lines of code, and then prove that there's no runtime error there. And then for the little ones that actually they care about really, really hard, then they do the formal with the spec. And there's no spec language in Rust yet, by the way.
So to put things in perspective, I know about symbolic execution, not about abstract execution. I'll come to you back later about this. Yeah. That said, when talking about formal proofs of this kind, usually, the system is semi-decidable. So it's very hard to always get a positive proof. how does it actually work in your system? Is the system so simple that it is not semi-decidable, or do you need to add some more information to the system so that it can actually get along and provide the proof?
So the grounds of using our solution is that you should exceptionally need to annotate the code. Exceptionally. So I can't say no, but in the 99.999% of the cases, it's just tool configuration. You don't change the code. In fact, that's actually an important thing. We work with some industrials already on the Rust language, and we already find bugs in things that they thought they could ship, and even in safe code. And they can't change the code anymore, except if it's a security issue. So that's the thing.
All right. Thank you, Aïssata. Thank you, Rolland, for our insights into making almost perfect code. So thank you so much.